volume is meter cube. You know the standard unit for length is meters. Unless the only time that you don't need to do that is if your question specifically requires it. Okay, so let's
Excuse me.
Yes, sir.
Emma, I think the unit was supposed to be Newton per meter squared.
Sorry, yes, Newton per meter squared. Sorry. You're correct.
Sorry, Emma, please, may I ask a question?
Yes.
Please, ma, this pressure volume work you gave us, when you said W equals to minus P delta V. Ma, when we solve a question, can there be a situation whereby the answer we get is positive?
Sure. What I was trying to say the other time. There's one example here. I don't think we'll get to it today because your time is against us now. I don't know. But let me explain that further. So how is work defined? Conventionally, work is defined is when you're defining it with respect to a system. So you define work as work done by the system. Why are you defining it with respect to the system? Because the system is what you're interested in. So when you are the system.
Wow, best last reminder about class. Abe, no start.
Work. If the external
I feel like what?
Yeah. Good morning, class.
Good morning, sir.
Yeah.
Good morning, sir.
This is physics 103 originally, but maybe some people may say it's 101. But you know, the coding is still being PHSY underscore CM, all those blah 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 of CC maths. But what we know that this is one of the topics for physics 101. So today we want to look at surface tension. Please, everybody should mute. If you want to talk or you want to ask questions, that's when you mute yourself. Don't want any disturbance. So the past 3 weeks, the other lecturers have been teaching, and this week another set of 3 lecturers will also start. I hope this is a medical class.
Yes, sir.
Yeah, yeah,
Yes, sir.
yeah. The other group, the other two lecturers are there. Then maybe after 1 week we interchange, which is the normal thing. It shouldn't be new to you now. So, the section we are now, as I say, is the surface tension. We want to know what is surface tension. We have been coming across this term maybe at various levels of your physics treatment, maybe SS1, SS2, SS3 physics. Even during the JAM preparations, you must have come across this term. Now, surface tension of a liquid, as you know, behaves as though it is covered by a stretched membrane. The strength of the membrane depends on the liquid. It is, for example, much higher for pure water than for soapy water. Surface tension is the property of a liquid, and the surface displayed by its acting as if it were a stretched elastic membrane. And this phenomenon can be observed in the nearly spherical shape of small drops of liquid and of soapy bubbles. These are what we come across every day. The behavior of the surface of the liquid, maybe as drops, or even when the liquid is not as pure as you said, maybe as soapy water, how the bubbles and all those things behave, the forces that act on them. That's what we want to look at. So because of this property, certain insects can stand on the surface of water. We have heard of this story many times. We always ask, what is the force or what is the phenomenon that allows an insect to walk on top of water? Normally, it's due to what? Surface tension. And also, a razor blade can be supported by the surface tension on water. The razor blade is not floating. If pushed through the surface, it sinks through the water. But all these are actions of surface tension on the surface of water. Then what are the causes of surface tension? Generally, we have these two forces we always talk about in surface tension, the cohesive forces and the adhesive forces. Now, due to the cohesive forces, a molecule is pulled equally in every direction by the neighboring liquid molecules. And this results in a net force of 0. Just like when you are doing a tug of war, this person is pulling from this side, another person is pulling from the other side. The net force is 0 because the forces that are pulling on the left and the right are equal. But when maybe the force that is on the right is greater than that on the left, the net force will now be but that of the right minus that of the left. Whatever that you have will be the net force. But when the two forces are equal, the net force will be 0. And that is what happens on the surface of a liquid when cohesive forces, a liquid is pulled equally in every direction. The keyword there, equal. So when they are equal, the resulting net force will be 0. The molecules at the surface do not have the same molecules on all sides, and therefore they are pulled inward. And this creates some internal pressure and forces liquid surface to contract to the minimum area. Now, there is also a tension parallel to the surface at the liquid air interface, which will resist an external force. And this is due to the cohesive nature of water molecules. And we have been talking about cohesion, cohesive nature. So later we'll define what do we mean by cohesive forces, or what do you mean by cohesion. Now, generally we define surface tension as the property of the surface of a liquid that allows it to resist an external force due to the cohesive nature of its molecules. We are still mentioning cohesive nature, cohesive forces. Anyway, no, you may already you know, but at least we'll do the definition later and distinguish the two, cohesive and adhesive. Now, surface tension depends mainly upon the forces of attraction between the particles within the given liquid and also upon the gas, solid, or liquid in contact with it. And we also said that surface tension is a force acting a line per unit length. If that parameter here, lambda, not lambda, gamma, is equals to F over L. Gamma here represents the surface tension, and F is the force, and L is the length. As you can see, that the unit is the Newton per meter. Newton represents that of the force, and meter represents that of the length. So if surface tension is F over L, hence the unit will be Newton per meter. Now, there are two forces of attraction for a liquid in a container. So let's now see those two forces. We have been mentioning cohesive forces. Now let's talk about the second one too. The forces of attraction acting between the molecules of same type are called cohesive forces. So if the forces are acting within molecules of the same type of molecule, we will say they are what? They are cohesively connected. That means cohesive force is acting on them because they are what? Molecules of the same type. But molecules of different types, the force that is acting on them is called adhesive forces. Adhesive forces. That's the force that acts on molecules of different types. But the one of the same type would be cohesive forces. For instance, if you pour water inside a cylinder or a glass cup, the molecules of water itself are held together by cohesive forces. But when, as you know now, when you pour water inside the glass cup, some water will now be on the glass, as we call the glass the water will wet the glass. We call it wetting of the glass. So the molecules of the glass and the molecules of the water will be held together by what we call the adhesive forces. So that's what we mean by the molecules of different types. So different types there is that of water and that of the glass. They are held together by the adhesive forces. But the molecules of water, which are of the same type, are held together by cohesive forces. Now, another quantity we mention here, or parameter we here, is the angle of contact. Angle of contact, the angle between the meniscus. Now, that's another term again we are mentioning here, meniscus. It may not be the first time you're hearing of it. In physics, your O level, you must heard of convex meniscus and concave meniscus. Like when you pour water in a test tube or in a glass cup or whatever, it will curve inward. The level of water will curve inward. And that is what we call the concave meniscus. But if you pour something like mercury, the curve will be different from that of water. But anyway, let's continue. As you even can see in the slide there, you have AB. The curve, that of A is that of water, and that of B is that of mercury. So when adhesive forces are greater than cohesive forces, the contact angle theta lies between 0 and 90 degrees. The first diagram you see there is when the adhesive forces are greater than cohesive forces. Contact force lies between 0 and 90. In geometry, we normally call it a acute angle between 0 and 90. But when the adhesive forces are smaller than cohesive forces, the contact angle theta lies between 90 and 180 degrees. That's the second diagram, between 90 and 180 degrees. So that's how we can, the relationship now between the contact angle and the two forces we mentioned, what's the name? The cohesive forces and adhesive forces. You can see how they are related now. When adhesive is greater than cohesive, the contact force, the range it lies between 0 and 90. But when cohesive is greater than adhesive, the contact angle lies between 90 and 180. Now, for liquids standing in a container, there will always be a meniscus. When you pour a liquid inside a container, meniscus forms. And it can either be, as I said before, can either be convex or concave. A concave meniscus or meniscus indicated that the molecules of the liquid have a stronger attraction. Please take note of that. Concave indicates that the molecules of the liquid have stronger attraction to the material of the container, which is what? Adhesion, than to each other. That's when you have cohesion. So convex meniscus indicate the molecules have a stronger attraction to each other than that of material. So as you can see here, a convex meniscus is that of A, and it shows that it have a stronger attraction to each other than to the material container. And here is that of B is for concave, as it were. Now, after that, we also, okay, before we move to capillary, let me ask, is there any questions so far? Yeah?
So that previous slide, the A, is it convex or concave?
A is concave.
You said?
A, is it convex or concave?
A is concave, as you can see now. Convex, sorry. Let's even start this way. In your physics practicals, you have concave mirror and convex mirror, is that not?
Yes, sir.
Yes, sir.
So that of the A and B, which one look like convex or even lens? Let's forget about mirror. Let's talk about lens. Which one look like concave? Which one look like convex?
A is concave.
Concave.
And B is
convex.
Yes.
so all these are what we already know. we know we have treated concave mirror, we have treated convex mirror. Okay, if it is types of mirror too, the same thing. A is what? Concave. Mirror. In terms of mirror, is A not concave? You're not answering.
Yes,
A
sir.
is
Yes, sir.
Yes, sir. A is concave.
A is concave.
Yes, sir.
And B is convex.
Yes, sir.
So why is somebody asking again, which of them is concave? As if you are not done physics. So I just want to use it to remind you of, we're just treating the same thing. Concave and convex means the same thing. Whether you're talking about the lens, or whether you're talking about the mirror, or whether we are talking about the meniscus in that water levels or mercury levels, they're all the same. Just that the shape of the when water rests on that container, the shape that it will trace will now tell you which type of force that is acting within the molecules. As I said, when the molecules have strong attraction to each other, it has a convex meniscus. But when it has strong attraction with that of another material, that's why water wet glass. Is that not? Water will have some attraction attraction with the material of the glass. That's why water will wet glass. But mercury will not wet glass because they will have more attraction to themselves. The molecules of mercury will have stronger attraction compared to the attraction with the test tube or the glass cup. Any other question?
Attraction to material to container than to the so why can reaction?
Any other question?
No, sir.
No,
Okay.
sir, right.
We'll continue. So capillary, and this is a tendency of a fluid to be raised or suppressed in a narrow tube. So when you talk about capillary, here we are somehow referring to a narrow tube because the pressure there will be more as to raise the fluid or the liquid or to suppress it. So, and that's what we call capillary action. That's movement of the fluid or in a narrow tube. Now, if a capillary tube is placed vertically into a liquid, as shown in the figure is in the other slide, the coming slide, capillary action will raise or suppress the liquid inside the tube, depending on the combination of substances. The actual effect depends on the relative strength of the cohesive and adhesive force. So here again, the cohesive and adhesive forces will come into play. If that angle we are talking about now is less than 90, remember what happens, which force that will be in play when we are between 0 and 90. If theta is between 0 and 90, what happens?
cohesive.
Please,
Can you mute yourself? Those of you that are talking, can you mute yourself?
I understand, but I'm like, maybe I speak another language. Kind of. Wow.
So if theta is less than 90, the fluid will be raised. If theta is greater than 90, it will be suppressed. So the implication is that mercury, for example, has a very large surface tension and a large contact angle with glass. So when placed in a tube, the surface of a column of mercury curves downward, just as like a drop. The curved surface of a liquid in a tube is called a meniscus. We have mentioned that. The tendency of surface tension is always to reduce the surface area. Surface tension flattens the curved liquid surface in a capillary tube. So this results in a downward force in mercury and an upward force in water. So as you can see, mercury, the forces of cohesion there are more. So they will always have the downward force, and that of water, the force of adhesion is more, and it will have an upward force. So water will rise in the capillary tube, the narrow tube, while that of the mercury, the reverse will be the case. So mercury is suppressed, as we said, in a glass tube because its contact angle is greater than 90. Then water is raised in a glass tube because the contact angle is nearly zero. Surface tension, therefore, exerts an upward force when it flattens the surface to reduce its area. This is just silent points we need to understand while treating surface tension, capillarity, that's a capillary action, and the forces of cohesion and adhesion. So now this is the diagram we are talking about. Capillary action, this one, for this is the concave meniscus. For convex meniscus, you have something like this. So we call this capillary repulsion. This is capillary attraction. This is for water, as you can see, and here is for mercury. Now, for the surface tension keeps the surface intact.
Excuse me, sir.
Yes, Emmanuel, what's the problem?
Please tell the people to mute their mic. They're making.
I've said it before that people should off their just mute yourself. I don't know. You know, in a large class, you always have in every 12 there will always be a Judas.
I want to my date.
Okay.
Your business. Yeah. My baby's day sometimes now, but I want to give them.
Please unmute yourself. Mute yourself. Mute yourself. Motolani, you have a question?
Like you should mute everybody. When you want to ask question, you can unmute us, and when you want to ask question, we raise our hand.
I know. I'm just trying to do that now. Thank you.
Huh? You have it. Agba. Agba.
So let's continue. I've muted everybody now, so we can continue. Anybody that want to ask a question, raise your hand, then I will unmute you. You will now ask your question. So I said the surface tension keeps the surface intact. So the whole liquid surface is dragged upward. Now the maximum height to which the liquid will rise through capillary action is given by H is equal to 2 gamma cos theta. H is the height. Gamma here is the surface tension. Rho is the density of the liquid. R is the radius of the tube. G is acceleration due to gravity. So that's the relationship now between the height and surface tension. Yes. What's the problem? Somebody raise his hand.
Yeah, good morning, sir. I want to ask a question.
What's the question?
The theta in the formula for height in this slide, how is it gotten?
Did you see the diagram we have here?
Yes.
Didn't you see the wait. The angle here. The angle inclined, the force is inclined to an angle. The force is not vertical. Can you see it? And look at the
Yes,
angle
sir.
here. Look at the angle here. So this angle here is equal to this angle here. Is that not?
Okay.
Haven't you seen the theta? Huh?
I've seen it, sir.
You have seen the theta.
Yes, sir.
So, and it's the same angle where this force is inclined.
Okay, sir. Thank you.
All right. Adetola?
Yes, sir.
What was it?
And the previous slide, you showed us when we were saying something about angle that is less than 90 and greater than 90. Is it the same angle? Yeah.
It has something. It has a relationship. But that's not where we are. Where we are now. That's when we are talking about the adhesive and cohesive forces.
Yes, sir.
Here we are under capillarity.
Okay, sir.
So we're not. It's not the same thing, but but it has some relationship because there's a way you can relate everything together here. Because
Okay.
but here we are talking about capillarity.
Yes, sir.
So we continue so that we will not waste our time. But at the end of the day, you can ask your question. So now another thing I mentioned before is weighting of glass. Weighting of glass. If you remember in our O-level physics, we say something like when we are treating the thermometric liquids. If you remember thermometric liquids, alcohol and mercury. We say one of the differences between alcohol and mercury is that mercury wets glass, if you remember. And it also has something to
Mercury
do
does
with
not
those.
wet glass.
Wet glass.
Huh?
Sorry, sir.
Mercury wets glass.
Alcohol, not mercury. Alcohol. Alcohol. Alcohol behaves like water, is that not? It wears glass. And what is the reason? The reason is that the forces of adhesion is greater than that of cohesion in alcohol or in water. That is the forces that the molecules of of alcohol and that of the glass is greater than the force between the molecules of alcohol itself. So that's why it wears glass. So wetting is the ability of liquids to form interfaces with solid surfaces. The angle theta between the liquid and the solid surface is a measure of the degree of wetting. So the smaller the contact angle and the smaller the surface tension result in a greater degree of wetting. As you can see from here, here the angle is 0. But as the angle here is less than that, between 0 and 90, you see the wetting it starts spreading. This one has the full spreading. The spreading will start reducing. And now when the angle is greater than 90, it now forms like a ball. That is, we are now moving into the mercury range, sort of. There's no wetting in that situation. That's why we call it de-wetting. As per DE, maybe with hyphen, then WETTING. That means you are moving out of the wetting scenario. So that is the issue of wetting of glass here, as per in terms of surface tension or capillarity, not capillarity, the adhesive and cohesive forces. Again, the angle, contact angle, I say, plays a great role. As you can see, they form situation where theta is less than 90, wetting occur. For situations where theta is greater than 90, there is no wetting of glass. So you can relate all these things together, the adhesive, cohesive, wetting, capillarity, and all those things, they are all interrelated. And the contact angle too, as I said. Another thing we want to also look at is the soap bubbles. Soap bubbles. That's another consequence of surface tension. So surface tension is the reason why liquids form bubbles and droplets. The inward surface tension force causes bubbles to be approximately spherical, and it raises the pressure of the gas trapped inside relative to atmospheric pressure outside. So it can be shown that the gauge pressure P inside the spherical bubble is given by 4 gamma over R. That's pressure is 4 gamma over R, where gamma, as you know, is the surface tension. R is the radius of the bubble. So bubbles has 2 surfaces, the inner and the outer surface, and the force from a surface tension, as you said, is equals to 2 gamma L. And a bubble can also be a spherical volume of gas inside a liquid. In this case, the pressure is given by 2 gamma over R. So we should note this, that for the inward surface tension causes bubbles to be approximately spherical and raises the pressure of the gas trapped inside relative to atmospheric pressure outside. It can be shown that the gauge angle P inside of a spherical bubble is 4 gamma over R, while inside the liquid, that of the liquid, the pressure is 2 gamma over R. Let's look at some examples. We are asked to calculate the pressure inside a soap bubble 2.0 times 10 minus 4 meter in radius using the surface, using the surface tension for soapy water as 0.0370. So just for us to quote the formula as we stated before, that it is 4 gamma over R, and that is 4 times 0.037 divided by the radius, and that gives us 740 Newton per meter squared. Remember that's the unit of pressure. Then Shizara.
Sir, please, I have a question.
Yeah.
The gamma that is there, is it a constant?
Gamma there is what? So what I've been saying, what have we been saying since? What is gamma?
Gamma is surface tension.
It's a value. I'm saying it's a constant. For a given surface, there's a surface tension. Surface tension is it equal all through? Huh? I'm asking you, Shizara, or who.
No, sir.
Yes, sir.
Your surface tension is not equal in all the surfaces, so it cannot be a constant. It's a value that's given to you that's the value of a surface tension. So that gamma there represents surface tension, and it was given for soapy water. So there may be surface tension for oil. There may be surface tension for pure water. There may be surface tension for some other liquid substances. So it's not a constant.
Okay, sir.
Farida, what's the question?
Okay, so in the previous slide, you gave us three formulas. One is this one, 4 gamma over R. Second one is F is equals to 2 gamma R. The third formula that is 2 gamma over R. When do we use that formula?
When you're given a question like that, you know the one when to use it. What do we say? You're asking of the one of 2 gamma over R.
Yes, sir. Because that one too is so bubble. I don't know.
Here, you say a bubble can also be a spherical volume of gas inside a liquid. Inside a liquid, do we say it's soapy?
Okay, sir. This one is for gas, sorry.
Oh.
Volume of gas. Okay. Thank you, sir.
All right. Another example that calculate the radius of a capillary tube that would raise soap 100 meters to the top of a giant redwood of surface tension 0.073, assuming that, sorry, that's sap, not soap. Sap's density is 1050 kilogram per meter cube. Its contact angle is 0, and its surface tension is the same as that of water at 20 degrees Celsius. Here we have already, in the previous slide, given the height. That place you talk about the angle. So the height was given as 2 gamma cos theta divided by rho gr. Rho, as you know, is the density, g is the acceleration due to gravity, and r is the radius. Just for you to now substitute the values given in this example and make r the subject of the formula, you can easily get your r. Remember here, theta was given to be 0. So, and our cos 0 is 1. And all those things. Just use your calculator and you can easily get your value of R. Forget this T here. This is supposed to be gamma, not T. That's for this the surface tension value. This is another example. A capillary tube of 0.05 cm, that's the bore, stands vertically in a wide vessel containing a liquid of surface tension 30 dyne per cm. That dyne, as you know, is an old unit of force, which you now have to convert. The liquid weights the tube and has a specific gravity of 0.8. Now, calculate the rise of the liquid in the tube. So the tension is giving us HR rho. Remember, tension is a form of a force. HR rho G over 2 cos theta. That surface tension is either you use that T or you still use our gamma. So it's still meaning the same thing. So that T there, remember, is just for surface tension and it's gamma. Because somebody will say, where did we get this formula from? This formula is from the normal one we have, as that gamma is that contains gamma in the previous slide. Now, we are told that theta is 0 and surface tension is 3.061 cm. For here, G is 980 because it will be easier for us to solve in cm because here it is 30 dyne per cm. So we can convert our acceleration due to gravity instead of 9.8 meters per second squared, we can use 980 centimeter per second squared. We are given that rho is 0.8 and T is 30 dyne per centimeter. R is where we are given the capillarity of the tube, which is equivalent to the diameter of the tube. So to get the radius now, it will be diameter divided by 2. So 0.05 divided by 2, and that will give us 0.025. So the substitutions are done there, and you have, this is another one too. Calculate the height to which a liquid will rise in a capillary tube of radius 0.02 cm when surface tension is 26 times 10 to the power minus 3 Newton per meter and density 800 kilogram per meter cube, and we're asked to take the angle of contact to be 0. The same thing, just do the substitutions and do the conversions if need be, like the radius that is 0.02 cm convert to meter, because every other thing is in SI unit, can now solve through. So most of those things here is that make sure that you solve with the same unit, not that one is in cm, another one is in meter. You want to solve in SI unit, convert everything to SI unit, and also leave your answer in SI unit. So it's very straightforward. Yeah. Another problem here, so almost the same thing too. So you have a lot, like here now, the density is given in gram per cubic centimeter. These are some old units that you need to convert. Radius also, or the diameter, the capillarity of the tube was given in millimeter. So that's the diameter, which you will have to find the radius and convert also either to cm or to meter, depending on where you want to work. Like here now, we work in centimeter, so we have to convert the millimeter to centimeter, so that everything will be appropriate. You can't just be solving in one unit and another, because here we have gram per centimeter cube. So we can also convert everything in centimeter and solve in that order, and leaving our answer in centimeter. So please take note of the units so that you will not mix it up. This is another example too. Here, ethyl alcohol rises 14.2 millimeter in a capillary of radius 0.4 millimeter. The contact angle is 0. Find the surface tension of ethyl alcohol. Abiodun, what's the question? Abiodun Oluwafemi. You are not talking again? Okay. So, Olaronke.
Sir, are we going to get slides?
He said?
Are we going to get the slides?
Well, I will find out how the other lecturer, were they able to give you slides?
Yes,
How
sir.
do you get? Huh?
Yes, sir.
Yes,
Yes,
sir.
sir. Sir.
Well, we'll look for her to get it across to you. It's
Thank
not
you,
a
sir.
problem. Yeah.
Yes, sir.
Thank you.
So here again, we are looking for the surface tension, the parameters given. You have to write them out and now get the formula, the appropriate formula. So you make gamma here, the formula to get substitute and get a very good calculator to get all these things done. So gamma here is 2.20 times 10 to the power minus 4 Newton per meter. It's another example again. Here we are asked to find the radius. So just to make R the formula from the expression for H and substitute the values given. Remember to convert any unit that is not in tandem with others, like the 20 millimeter converted to 2.0 times 10 raised to the power minus 2 meter. You can also convert back to millimeter your answer. If like that R is very small, 7.45 times 10 raised to the power minus 4, that can be also converted back to millimeter. So they are all simple and straightforward problems. Now we also have some MCQ, multiple choice questions. And this is some exercises you can do on your own. Now here, this one said, somebody, who is it? Deshino, what's the problem?
Good morning, sir.
Yeah.
Please, I want to ask if this is PHY 101 or 103 because there's another class happening right now, PHY also.
Which group are you supposed to be?
We are supposed to be in PHY 101.
Wait, which class are you? Are you a medical student?
No, I'm not a medical student, sir.
So that means you entered the wrong class. This class is
So
for
this is the
medical
wrong class.
students.
This is only for medical
For
students, sir.
you. Huh?
This is for only medical students.
There are 100 level classes are divided into 3. Are you aware of that?
No, we are not
If
aware,
people are
sir.
not aware, 100 level classes are divided into 3. There is a medical student, there is an engineering and environmental student, and there is science and education. These are the 3 groups. But they are being taught the same thing. So you understand
Okay.
now?
Okay. I'm in
You are being taught the
environmental
same
science.
thing. You are being taught the same thing. But environmental science, you are not supposed to be here. You're supposed to be in another group.
Okay. Okay.
But it
Thank you,
doesn't
sir.
matter unless if you are viewing from YouTube, it doesn't matter. It's the same topics they are being taught. But the only thing is that because of the population, you have to divide it into 3. So 3 lecturers are now handling it, but it's the same topics, the same everything you are being taught.
Okay.
Okay. So Onoja.
But sir,
Onoja,
according to
marvelous.
good morning,
Onoja,
sir.
marvelous.
Yes, sir, I'm talking. Sir, but
Oh,
according to the course outline we have, it is actually different. The courses, like the topics in each, because for like I'm a pharmacy student, we are doing physics 103, and we're also doing physics 101, and now we're having these classes at the same time.
you are confusing yourself. Let me tell you something. Are you listening now?
Yes, sir.
The course, maybe what you are seeing now is 101. Abi?
Yes, sir.
But 101 comprises of 101 is supposed to be part of 101 and 103. There's another course on its own that is 101.
Yes, sir. That is 101, and it's the class that is going on now. And now we are still on this medical class, which is physics 103, and we're also doing physics 101.
Why can't you listen?
So I'm
There's one
listening.
you had on Monday. There's physics course you had on Monday. Is that not?
Yes, sir.
Is it the same thing as this?
Yes, it's physics 103.
On Monday?
Yes.
On Monday is
On Monday is not 103. You are confusing yourself.
Monday is 101.
What Monday is 101?
But the thing is, we are doing the 2. So now that the class
You
is
are
not the
doing the
same
2.
time.
The one of 101 is on Monday. This is 103. This is on Wednesday. These are 2 different courses.
Sir, no.
You people are confusing yourself. You are just confusing yourself. Medical students. The subdean is the one that pasted this something to you. Is that not?
Yes, sir.
So what are you trying to confuse yourself? The one of 101 was on Monday. I think Monday or whatever, I don't know. But this one is Wednesdays and Fridays. 103 is one Wednesdays and Fridays. The problem is this is a new dispensation. If you don't know it now because of CC math. Well, let's end the class here now. On Friday, we continue because it's just 5 minutes to the time. Eh?
Take your question you were saying. You were sharing.
Which question you want to ask?
No, like you were showing something.
I mean, what I'm teaching or in your subject?
So, like you said, there are some questions you wanted to show us.
That I wanted to show you. That's the exercise, the MCQ that is on my screen. Are you not seeing my screen?
I'm saying so.
That's what I'm saying. We'll continue on Friday. Is that clear?
Yeah.
Or meanwhile, some of you need to go to the sub-team because whoever that is your class what's the name? Level advisor. To give you more information on this 103, 101 of a thing. Don't get confused. The two courses are compulsory for medical and all these people are called 103, 101. There are two different courses. The one you had on Monday and one other day. I don't know any other day you have it. And this one now is what?
It's Thursday.
Wednesday. I have Monday and Thursday. This one now is on
Yes.
Wednesdays and Fridays.
Yes.
So see you on Friday. Who is asking Nelly? What's the question?
Okay, hi, sir.
Nelly,
Sir, can you hear me?
Yes, I can hear you.
And sir, what are the remaining questions?
I say we'll continue on Friday.
Okay, sir. Yes, sir, but you will send the slide, sir.
Bye.
As I send the slide, though.
I will send the slides.
Okay, sir. Thank you, sir.
As I choose, I go. I just when I go, no internet, I just stop.